Our next speaker is Dr. Grant Willson. He's professor of chemical engineering at the University of Texas at Austin. He's going to give us a talk on high-resolution patterning, a view of the future. So let's welcome Dr. Grant Willson. Forward, backward.
What? Oh, yeah, I can see it. Okay, great. So my first slide is actually my commercial advertisement. This is the view from my office at the University of Texas at Austin. And I would be grateful if you would send your children to come to the university. It's a terrific place, and I'm very proud to be there. But I want to start by giving my thanks to Donis, to Harry, and to SPIE for the honor of this opportunity. I'm pleased to be able to speak to you and tell you a bit about what we do. I'll discuss making things smaller today, but before we start that, I want to say that I know it seems that I'll soon be turning 72, and I know that seems pretty old to you. And I'm often being asked these days, when will you retire? And I just want to give my answer, that's when I expire. I gave this talk back in 97, and I got here again, thank heaven. And Donna said it'd just be great if you'd invite me again when I'm 98. I just don't feel old at all, but when I look back, I see a long track. I actually started this kind of work in 1978. What were you doing on that date? We were making 2 kilobit memory that had a 4 micron gate CD. I know 2K doesn't sound like much today, but it's important for me to say that, hey, that's a whole lot more than the previous stuff, which was iron core. I don't know if any of you have ever even seen this stuff before. I've had a lot of fun along the way. This is actually a module of that iron core memory for those kids of you who have never seen it. It's actually wired together by hand. It's an amazing technology, and it was the basis of the IBM computers that were used in the space shuttle up until the very end of their flights. It's amazing stuff. Anyway, I've had fun along the way, and I'm still having a lot of fun today. And we've made resists, I guess, for about everything, it seems, from G-line to synchrotrons and electron beams. Some worked well and some were a mess, but what I will always remember best is not the solvent or the polymer goo, it's the people I worked with, many actually of you. I've had far more luck than the average guy, and I guess I'll never know just why, but one thing I know without a doubt, it's people, yes, people, it's all about. It's just a thrill beyond compare to see my students out there everywhere and doing as well as you can see. Oops, I missed something. As you can see, I guess all of you can remember Hiroshi. We lost that man. What can I say? We miss him each and every day. And then there's Dave Medeiros, IBM's litho czar. Now there's a chemist that's really gone far. And last week I was proud to see that Bob Allen was elected to the NAE. And last year I recall so well watching Bob and my student Mark Somerville give the best paper award to Shinyu Gu. Now that was something, I'm telling you. Because that boy Gu, he was my student too. Why should I quit? I'm telling you, I love my work and there's a lot to do. If I were to decide that I was through, I might miss the chance to meet the next Gu. Look, there are several of them here among us. So please see their talks and make a fuss. And ask hard questions and see how they do. You should find Julie and Chris and Ryan too. Search for Taka and Yuji, Logan, and Will. Oh my God, I don't want to think about that travel bill. But chase them down and say hello. They're terrific kids to get to know. And they come and work with me for a while to work with me, and then they go off to industry where they make things smaller, if you will, and then are asked to make them smaller still. Oh yes, and by the way, one of these kids may be your boss someday. So that's their job, to make things smaller, and I want to talk to you about doing that. I think I'm running out of time, so I'm going to give up the tortured rhyme, but their job is to make that stuff, as you see, and there's a man there standing on the top looking over them, watching to see if they do it right. And this is a man that all of you know well. He's in charge of making sure they do it fast and make it smaller. This is his famous law. It's not a law, it's just an economic fact. The fact is that if your company finds themselves in this bottom part of the plot, bad things will happen. There are many people who have found themselves there. But if you can stay up in this corner, you will be rewarded in important ways. And so this is what Moore's Law, I think, says. For us that work in this industry, or that work in our laboratories and so on, the issue is to stay on this inverse, if you will, of Moore's Law plot, that shows the changing dimensions with time. You can see back there where I started with the 4K memory. The process took place by playing with this famous equation, and there were major efforts made to monotonically reduce every factor in that equation that all of you know well. We went down the light path from 436 to 436 contact printing to 436 projection to I-line to 248 to 193, and then tried 157, and we failed. So we're never going any further than that. And of course, optical lithography has its limits. That K factor could be 0.25, but no one wants to push it beyond 0.3. The wavelength is not going to get smaller than 193, and the sine has a maximum of 1, and you need some room to wiggle, so that means minimum resolution 65 nanometers. This is a scary thing. That's not a good sign. Something bad will happen if we don't find a way to fix that. Thank goodness, if this is the end, we're in a world of trouble. But along came an angel in the form of Dr. Lin, who saved us with his healing waters. He taught us that if you look closely at that equation, there's actually more detail to the denominator than many had considered, and that if we still had something we could play with, which was that lowercase n. So we changed n from 1 to 1.4 and pushed the resolution down to 45. Cool. Unfortunately, 45 does not equal 22, and that's where we need to go. So this time, maybe it's for real. This could be the end of the line. Who will save us this time? Somebody's got to save us. Is it this person? I guess we're all hoping so. Being old means you collect a lot of junk, and one of the things I was rooting through my junk, and I found this interesting slide from Peter Silverman. You all remember Peter Silverman? He wore a bow tie, actually. And the date of this thing is quite old, and it's got some interesting things on it that we should pay attention to, I guess. Here is I guess we're a little late. But there's still hope. Because in this slide, you see that we're projected to have, by 2010, that we would be running at 60 wafers an hour. Well, I don't know, hope is fading. It's a large and complex and costly solution. I mean, you don't need to go much further than to realize that that's just the light bulb for the thing. And the cost of it, of course, our previous speaker was arguing about cost. This thing says that the price of the machine will be $125 million. I don't think that counts the track and a variety of the other things that are required to do it. So as Mark says, don't choke. But I have to say basically that I am increasingly of the opinion that the rate of technological progress is going to be controlled from financial realities. We just can't go as fast as we'd like because we can't afford it. And in spite of your best technical contributions, when we're looking at new technology, please look at how to make that technology affordable as well as functional. That's actually a quote from Gordon Moore in his paper that was the plenary talk, this talk, given in 1995. I was the chairman of the conference that year. I invited him to come and speak. He said he wouldn't do it. I badgered and begged him, and he finally explained to me that the reason he didn't want to speak is he didn't want to produce the paper. So we hired a stenographer to take notes of what he said and stuck his slides in and generated that document. And it's fascinating to read. Wonderful piece of projected suggestion of where the industry is going and incredibly accurate. This couldn't be more apropos, the statement that he made in 1995. So the only option, I guess, left is for us was double exposure. You can't print it close together, so you print two of them and push them together. Of course, you can see that my PowerPoint skills are not perfect, but you can imagine what a challenge it is to align these things in real life. Amazingly, people can do it, and they're doing it well. And you can print remarkable structures this way, very far below the resolution limits of the tools. It's a tribute to the tool makers that the alignment of that is possible. The chemists and resist people have taught us how to do a wide number of techniques that enable this technology. Litho-freeze, litho-etch, litho-etch, spacer gap, and so forth. We won't spend time today talking about those things, but they have a common characteristic is that they're expensive, and they require more tools and more steps than traditional single-cycle exposure and development. And so the question is, can this be made cheaper? Clearly, we're going to keep doing optical lithography, and we're going to do it at 193 for a while. So our goal was to see if we could make it cheaper. I'll tell you quickly about our attempts to do that. The resists that are being made today are incredible. This is the performance of a commercial eyeline 193 nanometer resist. You see it has an absolutely threshold-like onset of solubility. You can expose it for a long time, and then suddenly, over a very narrow dose range, it increases 5 orders of magnitude in its dissolution rate. It's a remarkable thing. The fact that it has this sharp threshold response, and that we name E0, enables us to do something that's fun. The double patterning process involves printing once with the mask, then moving the mask and doing a bunch of other tricky things, and then printing again. And that's expensive. So the question was, wouldn't it be cool if you could print once and automatically produce 2 images at the same time instead of 1? Obviously, I wouldn't be showing you this if we hadn't found some way to do that. That is to get twice as many spaces on the wafer as you get on the mask by using chemistry instead of optics. This would push K. So the way we do that is easy to understand, I think. Typical aerial image has the shape you see here. It's essentially a sinusoidal function. And the E0 is such that when the dose crosses that threshold, the material becomes soluble. And you have if everything is set right, you can duplicate the pattern on the mask. If you set things as we had done before, but then induce into the resist a negative tone threshold at higher dose, then in principle you should be able to print a negative tone image in between each positive tone image, and thereby double the pitch of the mask. And so that's an attractive thing to try and do, and others had done it before in various ways, but we decided that we would try it. So the students came up with the idea that one could do this if they could design a system in which the acid generation curve, instead of being classical first order in behavior, was such that as you increase dose, you would increase the acid concentration, and then with increasing dose, you would destroy the acid in some way, and the concentration would drop back across the threshold to produce a negative response at higher dose. So to make this happen, we just needed a way to achieve this kind of acid dose response. And that was done by incorporating a photoacid generator and a photo-base generator into the resist formulation, such that the photo-base generator generates base, which kills acid. By adjusting the relative rates of these two things such that the rate of acid generation is faster than the rate of base generation, but the total amount of photo-base generator exceeds that of the acid generator, you shine light on the thing and all this starts to happen simultaneously. And if you look at this one little piece down at the beginning where things are important, you see that in this region that's colored, there is excess acid, and for all doses above that, there is excess base. So if I take that area and lay it down, my goodness, it looks sort of like the cartoon that the kid drew about the way of achieving this phenomenon. So sure enough, student Xinyu Gu mixed all these things up and ran the experiment, and the very first time he ran the experiment, my goodness, he got this kind of result. That's the sort of thing that hasn't happened very often in one's career. This is where you can't sleep, you can't understand what your wife is saying to you. Very exciting time. So we were happy to see that the material performed in the way expected. And as Xinyu showed last year, we sent the stuff to Intel. They printed it with a 440 nanometer pitch aerial image and quickly got a 220 nanometer pitch image. So it successfully doubled the pitch of the mask. That gives a K of 0.15. So by doing this, you can actually break the limit for K if you could make it work right. He also reported having taken commercial resists and just mixing some white powder in there, stirring it up, and causing the commercial resist to behave in this way as well, such that 90 nanometer pitch aerial image would produce 45 nanometer pitch lines. Unfortunately, the good news is that K is 0.126. The bad news is the lineage roughness is nasty, and the images are ugly once you calm down and look at them closely. So we think that the reason for that is because the acid generation curve for the dual tone system is the slopes are degraded relative to the acid generation curves in normal resist, and therefore the contrast at the line edge suffers. So to try and fix this, that slope, reduced slope is not a good thing. So to try and fix this, we have designed a method of changing the kinetics of the photo-base generator such that instead of just having light produce base, you have light produce a photo-base generator and then have the photo-base generator produce base. And that produces the sort of quadratic-like structure that you see on the right. Doing that by simulation dramatically increases the slope of both the negative and the positive piece of the acid curve response, which is good news. And if you'll visit the talk of Ryan Mesh, my student, who's in poster is there, he'll show you the result. I dare not to steal Ryan's thunder, but I'll tell you that it's a exciting piece of work. Will this work? Well, I don't know. Great students are working hard on it. And please see their poster and their talk on this topic, and you can judge for yourself whether it looks promising. So what about DSA? We've got to go further. This will only take us to a factor of 2 better than the natural pitch of the tool. So what about DSA? Can chemists help with DSA? Impressive stuff. I think this was, from my personal opinion, one of the most important papers given last year. It was a paper given by Chris Bencher describing work that he did in collaboration with IBM using directed self-assembly to do full wafer experiments. It was terrific stuff, very impressive. And he's got a paper this year you should be sure to see. The driving force for this is hidden in this phase diagram that we need to take 1 second to look at. What it's telling us is in the horizontal axis is something called the volume fraction. It's essentially, for simplicity, the relative length of the two blocks, approximately. It's related to that at any rate. For intuition, it helps to do that. On the other axis, the vertical axis, there are two factors listed, chi and n. Chi is an interaction parameter, which describes how the two blocks interact with one another. If they hate each other, like oil and water, the number is high. If they like each other, like typical organic compounds, then the number is smaller. And the letter n is the length of the chain, effectively. So if you want to make small structures, like small cylinders or small lamella, what you want is to have n be small. The length of the chain has to be small in order for the structures to be small. If the length of the chain is small, then you have to have chi be big, because the product of chi and n must exceed 10.5 in order to get into even the condition where there's a phase separation occurring. So we want a large chi, and we want small n's in order to make small structures. One of the attempts we made to achieve this was to get as close as we could to oil and water. We found a collaborator in France who works with sugars. Sugar has a empirical formula of CH2O. It's about as close to being water as you can get. And he can make monodisperse sugar oligomers out of naturally occurring starting materials. And Julie, the young lady on the right, will be giving a poster today talking about this, or later in the week talking about this work. And she made oil, which contains some silicon, actually, trimethylsilylstyrene. And they joined the two things together and made this interesting sugar block copolymer, which will be described in Dr. Ellison's talk and in Julie's talk that are listed here. I encourage you to visit them. And I think they've made the smallest structures that have been made. They're about 5 nanometer diameter objects that look pretty interesting. They're very new. We haven't succeeded in doing a great job of etch transferring them, but you'll hear about this work in Dr. Ellison's and Julie Cushion's talk. The last thing is that what we're doing in this area is trying to solve a problem of alignment. It turns out that we developed a process that involves first coating the surface that you're going to put the block copolymer on with a specially tailored layer that has to have surface energy that's halfway between the two blocks. This is well known. Many people have described this. If you can achieve that and you cross-link that so it doesn't get bothered by spin coating the block copolymer, then when you heat the polymer, it'll stand up if you're lucky, and the lamella will stand up or the cylinders will stand up. Unfortunately, when you have one of the blocks itself has a very low surface energy, it sees air. And when it sees the air, the bottom of the wafer is okay. It's happy to stand up on the basis of what's on the bottom of the wafer, but it looks up and it sees air, and it doesn't like that. It wants to put its low surface energy block up against the air, and you have a big fight. So we need an alignment layer on the top as well. And we've learned how to do that by making so-called top surface alignment layers and by vapor depositing them. And those papers are described here in the poster sessions number 90, 91, and 92. Essentially, the trick is that you can't spin coat just any old thing on top of the block copolymer. In particular, you can't spin coat a random copolymer because any solvent that would dissolve it would also dissolve the block copolymer. So we need something that switches its surface energy and allows us to coat out of water. In this case, we use, one example of what we're doing is taking anhydride polymers, which are relatively low surface energy, and then you dissolve them in ammonia. They open up and become water soluble. You spin coat it and then bake it. The ring closes back up again, and the top layer has surface energy again matched to that of the block copolymer, and by Jove, the thing stands up, and then you can just wash it off again with base. So here's the process that we are doing, using this top coat to get the stuff to line up, and we have a perfect surrogate for this. We have a block copolymer that literally will not stand up no matter what you do to the bottom layer. But sure enough, when you put the top layer on, it says, thank you, I don't have to feel the air, and it does stand up. So this is some pretty exciting and I think new stuff that you'll see in the poster of the students that was listed there. There's really no, there really is ultimately some limit to how we can continue to shrink. This is it. This is the limit. This was done by my colleague, Don Eigler, when I was at IBM. It was done just south of here on Bernal Road at the Almaden Research Center. One atom moved by scanning tunneling microscopy. And here it is on Don Tennett's famous plot. It's down in the lower left-hand corner where the ultimate resolution, one atom. It's also the minimum throughput. It takes 1 minute to move each of those pixels, one atom. In the upper right-hand corner is photolithography. Tremendous information transfer rate, but throughput, but the resolution, as we saw a few minutes ago, is limited. And everything that's in between seems to fall in a line. Don found this correlation, it's very cool, except one thing, and that's Imprint, which is off the chart, down and to the right, in a place that otherwise cannot be accessed. That's exciting to me, and that was inspiration to work on this project with lots of others. And we developed at UT and this method, which is now commercialized at Molecular Imprints. We use a transparent template with relief structures etched in it. The template's expensive and hard to make, but it's made by standard mask blank processing techniques. And I use an inkjet printer to spritz down some polymerizable liquid. We capture the liquid between the template and the substrate, and then convert it from a liquid to a solid by shining light on it. It's not focused light, it's just broadband illumination, cheap. And then we can just step and repeat this process to populate a wafer. I think many of you have seen this work. It's making great progress, and the disk drive people have expressed a great deal of interest in it, and it certainly looks like the great solution for doing bit pattern media. I contend that the highest resolution lithography that's being done today is being done not by the semiconductor companies, but by the hard disk drive companies who are using block copolymer magnification of e-beam written patterns to create imprint templates and then processing those templates in the way you see here. There's a nice talk about this work to be given by Mark Miller-Smith later in the program. I encourage you to attend his talk on Wednesday. Some exciting and very, very terrific stuff. This is very small. These are very small structures that are being made by these techniques, and fun to see. Molecular Imprints has, for over a decade now, worked to commercialize these tools. It's been an interesting undertaking. The company is actually supported, and venture capital funding has been provided by many people, including major semiconductor chip manufacturers. But when they give money to this company, they only give it with the proviso that you're forbidden to ever tell anybody who gave you them that they're associated with you. It's like they were dealing with prostitutes or some other kind. I mean, you dare not to imprint. This is evil. So it's been fascinating, absolutely fascinating. So there's a whole history of the development of these tools. The thing that has happened with it most recently that's important is that first the tools were all being made in Austin and exercised all over the world, but a Japanese manufacturer, Toshiba, decided they would give this a major try. So they made a deal with Molecular Imprints and told them that, listen, I don't want to buy any manufacturing tool from any small weird company in Austin. It has to come from a Japanese company. And when I dial 1-800, it won't print. I want someone speaking Japanese to answer this phone, and so forth and so on. So a deal was made with a Japanese tool company to provide imprint tools to Toshiba. And now what's happening is Molecular Imprints builds a module, which is just the guts of the tool, and it's being shipped to a Japanese tool company supplier, whose name I'm forbidden to say. And they, in turn, integrate it into their system, and they provide the tool to customers. The first customer that they provided it to is Toshiba. And the hope is, here is the picture of the module, and it's sort of the equivalent of the lens. That is, in an ASML does not make lenses. ASML makes products that they buy the lens from Leica. And so the same thing is happening here. The company that's supplying the tool buys this module from Molecular Imprints and installs it into their tool. The size of that lens, you see the person behind it, is quite a bit larger than the module from Molecular Imprints. That module thing is about 1.5 feet or 2 feet, 1.5 feet tall, and you can judge its size from that. It's a complicated and very sophisticated piece of machinery, but it's not a large piece. So what's happening in this field? In the last year, Toshiba described some work on their alignment. They demonstrated 10 nanometer 3 sigma mix and match to 193. That was last year. I haven't seen their data this year. The kind of CD uniformity that the tools can provide is legendary, actually. It's really very small. Whatever is on the template is printed every time exactly the same. Incredible characteristic of this kind of printing. It looks great, right? But what about defects? This is what everybody wants to know about. Well, there's some wonderful information about defects. I wish I could tell you this information, but I'm not allowed to tell you this information. But if you go to this panel discussion, the Higashiki-san from Toshiba will tell you something very exciting about defects in imprint lithography. I encourage you strongly to attend that thing, and I wish I could tell you, but I dare not to steal his result. The one thing I can tell you is that it's continuing to trend downward. It's like all technology of this sort, when you get down to the end, it's one after another finding the tiny contributors to the generation of defects. At one point, we found nickel in all of the defects that were on the wafers. Nickel. There's no nickel in our machine. So great detective work was done and discovered that there was nickel in the inkjet dispense tool, and that somehow this inkjet dispense tool was periodically burping nickel balls. So we had to go and talk to the inkjet vendor and get that one fixed. It's just a slow evolution of reduction of the sources of defects. And filtering the resist material turned out to be a major issue and is continuing to be, but it's improving continuously, and it's down to the stage where you need to see the Toshiba work, which is testing the defect density with electrical tests. It's very impressive. Where is this technology? I notice it's not even on Qualcomm's map, right? Because it's, I don't know, prostitute. They had Mapper, but they didn't have us, right? It's close. Take a look. Everything is cool. The defect problem is there, needs to be solved, but it's rapidly resolving. And I encourage you to visit this panel discussion that'll take place at 5 o'clock on tomorrow. It should be really, really interesting. So there are several related talks in the conference that I want to invite Qualcomm and everybody else to visit that talk about the mask making infrastructure, the work on CMOS memory, new work on mobile displays, and some wonderful things that are going on, and very high resolution lithography for hard disk drives. Lastly, let me leave you by saying, you know, this is a picture of what's at Albany. There's a EUV tool installed there, the one on the left, and there's a very early version of the Imprint tool installed, the one on the right. And there is the baby picture of the tool on the left, and there's the baby picture of the tool on the right. And the one on the left has an electric power plug that's about as thick as your arm, and the one on the right plugs into the wall. I don't know what this means, but it's certainly interesting. I think the biggest challenge for Imprint is not technical, it's psychological or sociological or something like that. It's very, very interesting to watch and to see how the thing evolves. So I'm saying no, Homer, the race is not over. Imprint is making great progress in Japan, and if workable, it surely might be the lowest cost alternative. There are a number of exciting pathways to sub-20 nanometer imaging, including the sidewall patterning technique, which looks really attractive to me these days. That stuff that Bencher did impressed me, and I continue to be impressed. But the cost of patterning is becoming a critical issue. And that is the message of both of these talks, that our job is not only to make them small, but to make them cheap. Thank you very much.